Another thing to point out, so you notice, for example, here, I use this little extra code factor. So that's because model matrix can also include those continuous covariates predictors. And rep just happens to be coded in the data set 1 and 2, right? So if I didn't put this, so this factor is making R know that rep is not a continuous predictor. Rep is a factor. Rep has levels. There's no, it doesn't make sense that rep 2 is more than rep 1. In other words, it could be rep A and rep B, rep Bob and rep John. It doesn't matter. So location is already a factor if you look at the structure of the data set. Because locations have A, B, and C. It might also be a character, and if it's a character variable, then R is already going to know what's going on. So later, for example, if we do this for a SNP data set, you would not use factor because SNPs are continuous predictors. Okay, so we now have X, we now have the Z matrix, the last one. I've chosen a phenotype. You could choose a different phenotype. I think one of the more interesting things to do later, in fact, when I went through this, I didn't test the other phenotypes, so you can feel free. Right here, I'm making a vector from the phenotypes training data set that corresponds to, this is cassava brown streak disease severity, you care to know. So I've just picked a phenotype, and now we're going to be ready to do mixed solve, which is down here. Bring this where I can point at it. Okay, so mixed solve. Actually, does everybody know how to look at the help files for an R package? If you don't, you type the question mark and then the name of the package. That's really small here, so I think we can. I just want to make sure everybody knows because I work in R every day and I still use these. I don't have everything memorized by any means. So this will remind you what has to go in or what the options are for any thing. So mixed solve needs to know the Y vector. So it's just solving the mixed model that we started with, right? So it's looking for these things, right? So it needs Z, it needs X, and it needs Y. Well, and it can sometimes also need, so a covariance matrix. Actually, we'll get into that later. So to do ridge regression, we're going to give it Y, we're going to give it Z, and we're going to give it X. Okay? And there are some other options that if you get really fancy with it, you can look at later, okay? And there's one, right, I'm realizing these things as I go along. So we made a Z matrix that relates the observations in the phenotype data set to the rows of the SNP marker matrix. And so here, to give it Z, we want to give it the SNP markers, and we want to basically have a SNP marker matrix that has one row for every phenotypic observation. So it's going to have duplicate rows, right? If you have 3 observations on the same individual, that individual's genotype should have 3 rows. And so we do the Z, and then this %* is telling R to do matrix multiplication times m.trn, and that is the training SNP data set. So that's the subset of the centered marker matrix that we made earlier. And so you do this, and you just get a matrix that's n observations by number of SNPs on the column. Make sense? And then you could just do our first prediction. So this runs mixed solve. I'm not sure how long that'll take on everyone's computer. Okay, it's running.
which of these functions are within our world package? Model matrix?
Model matrix is the base. Actually, mixsolve is the first thing that we've used in the RR package. So the next thing I do is just a plot, because we want to see our marker effects, something nice. So this should just make a line plot of the squared marker effects. And actually, if you go back to that help file, it also gives you a list of what the outputs will be from any given function. So this is a little bit squished. But so you see you have a couple of outputs from mixsolve. That looks a little bit more squished here, but you have VU. This is your estimated variance in marker effects. This is your error variance. This beta object is going to contain a vector of the fixed effects, so the locations and the reps. Then you see it's 1,000 long, and it contains the SNP marker effects. And so when I run this bar plot function, and that's built into R, it's plotting, and I chose to do the squared marker effects. You could also, that's just so that they all have non-zero or non-negative numbers. That's interesting. I'm having a problem with my projector here. So does everybody see a plot of marker effects? Because I don't.
Yeah, it's just your window.
It's too small. I think so. I'm not sure if I'm going to be able to make it large enough. There we go. Okay, so everybody should see something like this. So in practice, there's not really too much reason to look at this. I kind of like it. It's not quite the same thing as GWAS, but you can kind of see. And I'll admit, I kind of spiked the data set to make sure that QTLs I knew existed are in there. So we got something, I think this is on chromosome 4, and you could see how you get a big marker effect here. Maybe there's something over here. Ultimately, again, the point is we use all the markers. So pay not too much attention to these things. But one of the things to do with plotting these as we go is you can see, because we'll do the same trait and the same data set with different models, how the sort of distribution of these effects are going to differ between models, especially when we do like the, if we get into the Bayesian models later. So yeah.
The y-axis is the effect, right?
Yes.
Okay.
And then so the x-axis is actually the SNP markers, which happen to be in order. So this is effectively a plot of the location of marker effects on the genome. Actually, the y-axis is the squared marker effect. So let me show you what the raw marker effects look like, because some of them are negative, right? Some markers have a decreasing effect on the phenotype, others an increasing. So this is what the raw marker effects look like, right? So negative effects, bunch of stuff, centered on 0. And then there's one more line here. This is something I don't normally look at, but I wanted to give you a way. In a moment, we're going to do a relationship-based model. And what we get is one of the handy things with doing these models is they provide you with an estimate of the additive genetic variance that markers can explain. In this case, when we do ridge regression, the variance that we estimate is the variance in marker effects. So it's not quite the same thing. So you can use, so when we do the relationship-based matrix one version, the GBLUP model, VU is going to be our additive genetic variance. And so we'll be able to calculate an estimate of the heritability in the data set. In this case, this is not your additive genetic variance, but you can calculate that from this. And so I put this little formula in here. So this is 2 times the sum of PQ, the frequency of the major and the minor allele, times this variance, and this gives you a number, 0.75, which is your genetic variance. So if you take this number, so then you could do, and you get an estimate of heritability from markers. Does that make sense? Yeah.
So, I don't know if this would play a role in this, but are you getting some type of sort of Beavis effect by summing up the value of all of these markers? Because some of the markers are probably overestimated. I don't know if that'd be true using Richter's. But I would guess that the heritability you calculate there would not be the same heritability as if you were to calculate, the phenotypic additive variance over the total variance.
No. I think that that's actually because we have fixed effects in the model, and they do affect the variability. So you could just calculate, I have to look at that. So if you just calculate the variance in the phenotype, the CBST phenotype, we could see if they match, would be interesting. I think a lot of times we are interested in the sort of ratio when you've removed all the sort of like location effects anyways, because it tells you something. It's something more equivalent to like when you do the heritability with the error variance divided by rep sort of thing. Sorry, that's something that's new to me because I've only been in plant breeding for 2 years.
The Beavis effect is basically if you're to map QTL and look at the effect of each of those QTL and add all those up, it's greater than the actual phenotypic variance there.
So we've done the shrinkage to avoid that.
Okay,
So
that was my question.
Right, so that is what the shrinkage is for. I mean, we do need to use the caveat that this is heritability that is explainable by markers. So for example here, I've only used 1,000 markers. Normally the data set started with 180,000, which is, so when you have a smaller coverage, I'm probably missing stuff here. But all these like, there's a lot of like papers, like Peter Vischer's group doing analyses in humans where they're trying to explain heritability using markers packed across the genome. And that's what we can do here. And these are similar models that they use. Okay. So is everyone pretty much on board here? I have like another 2 PowerPoint slides or something to show you to relate this ridge regression to the relationship-based model GBLUP. Any questions? Okay, so the next model that we're going to fit is also going to use mix-solve. There's actually several different R packages we can use to fit the GBLUP model. And it makes, if you formulate it in the correct way, it makes equivalent predictions of genotypic value to the ridge regression. But this is a model on the lines instead of a model on the markers. So we're not going to estimate marker effects. Instead, we're going to calculate a relationship matrix based on the markers. Okay, so it's still a mixed model, just as before, which is why we're still going to be able to use mix-solve to solve it. So fixed effects are the same, error and Y are the same. But now, instead, ZG becomes a factor that corresponds. It's going to have the number of levels that there are lines. And that's actually going to be lines that are in your relationship matrix, whether that's all the lines that are phenotyped, so just the training set, or all the lines, training plus test. So Z is now just an incidence matrix that relates the phenotypic observations to the rows and columns of a covariance matrix, which we'll calculate using the markers. So before, this Z was the marker matrix. It was the covariates, the marker predictors. Okay. Now G estimates the BLUPs for each individual, which correspond to what is going to happen when you multiply the marker. So in ridge regression, you multiply the marker effects by the marker scores for each individual. You sum them up, and you get the same value that you're going to get out of this model. Because here we have a small difference in the assumption we're making about the random effect. So we're still saying that the effects, that is the breeding values in this case, are drawn from a normal distribution. They have a mean of 0 and a certain variance, which is now going to correspond to the additive genetic variance. And now instead of I, so we didn't have any covariance matrix between marker effects in ridge regression. Now we have a covariance matrix. And again, that's what we calculate with the markers. So, and okay, so I have this one other slide to go back to the incidence matrices. We already made this. This is what we did in ridge regression. The incidence matrix contains the predictors, right? So these are the marker dosages. And then you can see the contrast. So for GBLUP, now this just relates. This is going to have phenotypic observations, but relate them to which row of the kinship matrix that individual's relationships correspond to. Does that make some sense? Okay. Might make more sense with...
Well, I'm not sure everybody here would know what kinship matrix is necessarily either.
Right. Well, Dooney and I flipped things around a little, and we were going to start out with making kinship matrices. So we can come back and think about this later. Okay, so we have our centered marker matrix, which is what we use to make predictions in ridge regression, right? So that has individuals on the rows and markers on the columns, and we called this M. So we can do a simple thing. M times the transpose of M gives you a covariance matrix. So this is just a nice matrix algebra trick. I'm not going to try to go into the details, but so this gives you a covariance between individuals based on certain predictors, and these predictors are just the markers. So what it's going to, the dimensions of this thing are going to be number of individuals by number of individuals. So this is a square matrix. It's symmetrical. I actually kind of had this, we often plot, we'll make a little figure that shows a relationship matrix, and here the values in this matrix are just colored. So white colors are strong relationships. Dark colors, I know you can barely see this, are lower relationships, smaller relationships. Maybe when we come back from the break, I think Dunia, you have some slides that'll be helpful. But what this matrix contains is on the diagonals, we have something that's equivalent to 1 plus the inbreeding coefficient. At the moment, what this does is actually it's equivalent to counting up the number of homozygous loci. And then the off diagonals, it's relating individuals to each other. So if you have ever made a correlation matrix between, say, traits or locations or whatever you might do, this is equivalent. We're just talking about the correlation based on markers between individuals. So how genetically similar each individual is to each other. So these off diagonals count up the number of shared alleles between individuals. So if this is individual 1, and this is row 1, and this is, column 1 and row 4, then this would be the relationship coefficient between individual 1 and individual 4. And that corresponds to the number of alleles that they share with each other across the, in this case, 1,000 loci. Does that make sense?
It's a very straightforward measure of genetic distance. It's not kinship.
That is kinship.
This kinship is weighted based on how valuable the alleles are, how rare the alleles are. So rare allele will add much more value in kinship matrix than genetic distance matrix.
You got it. And that's why I used M here. So in M, what we've done is we've centered. So, so I'm sorry. Thank you for making sure I don't get ahead of everyone. So one of the first things we did is this centering. So we started with, often we use Z to be the marker matrix. So the one where it's just 0, 1s, 2s. But since the alleles differ in their allele, the markers differ in their allele frequency, we don't want, so that's going to mean that markers with a higher allele frequency that are more common are going to have a lot more weight. But since we're really trying, like you said, to measure kinship, and we don't want to lose those rare alleles, we want to give them equal weight in the relationship. We want to make it a fair competition. We do this centering across the markers. And so when you center Z, it becomes this M. And so this makes this a kinship measure. Here's one little thing that I haven't put on here, and usually this, this covariance matrix is scaled by a single number. And so this just has the property of putting it on a scale that makes it more related to pedigree matrix. So since we're not going to look at pedigree matrices, it doesn't matter too much, but it's just 2 times the sum of the 2 times the sum of PQ, or P times 1 minus P across all the markers. Does that make sense? So this is just a single number, a scalar, that we divide every number in here for, so it doesn't really change any relative relationships. So most of what's going on is based on this M times M transpose that gives you these measures. And we can create, so what we'll do is we'll create this in R, and then we can look at it. We can even make a little heat map, something like this, so you can see the relationships for yourself. You can see the distribution of inbreeding coefficients. So you can kind of see what's going on in this thing. So then it's just fitting a mixed model where you have effectively a clone effect, where clones have covariance between each other that's according to how closely related they are. So we're conditioning how close their predictions should be to each other on their genetic similarity. And I can try lots of different ways to explain that, but maybe there's cookies and coffee, and we should take a break. Right. That's pretty much, from here I did more R. Or we can keep going.
Yeah, nothing more than that, but I'm assuming we're having.
Oh. Okay. So I also put this in here. These are the mixed model equations. I'm not going to go over them. It's for your reference. You'll see this stuff a lot. These are just the solutions to these. So what we're going to do now is make a kinship matrix, and then we have 2 functions in the RBLUP package that can do GBLUP. The first is mixsolve, which we just used. We're just going to use it in a slightly different way. And then the second is kinblup, and it's just a wrapper. It just has a nicer user interface for doing GBLUP, but it doesn't do ridge regression. And then the last thing we'll do in this part is compare the results, because like I promised you, they produce identical results. And so that's kind of an interesting thing to see. And there are different reasons you might use the marker-based versus the relationship-based approach to making predictions. But at least in this formulation, they give you the same answer. So we can go to R again, and we have section 2. So we're going to do gblup and mix solve, but first we have to make a relationship matrix. And so I actually have 2 lines here to show that actually produce the same relationship matrix. So this is kind of the manual way. So I just wanted to show you. It's actually doing what I just wrote up here on the board. So we have the marker-centered relationship matrix. In this case, just for the training data set, times T is just telling R to do the transpose of the relationship matrix. And then we divide it by the sum of 2 times the column means, which happens to be equivalent to this value here. But then I also wanted to show you a.mat, which is another function in the RBLUP package, which does this behind the scenes. So it's a nice handy function. And the only thing that I have to note with it is it actually wants markers that are coded -1, 0, 1. So you have to make sure, and this is why you should always look at the help package for any R function, right? So it'll tell you it wants markers scored -1, 0, 1. So all we do here is subtract 1 from the data set. Actually, this should be M, I believe. No. This should not be M because it will do the centering for us. So this is why I give snips.trn here, and that's why I made this matrix in the first place. So this is going to do the centering, make this M matrix for you, and then do this division here as well. So you can run both, or either. You could create a duplicate matrix if you want to compare them. They should give the same result. But since we're talking about what's in this matrix, I want to show you what it produces. So I'm going to do a few things. There's this function heat map that's handy in R. This is built in. And if you do a heat map of K, you have to tell it a little option to tell it's a symmetrical matrix, just so it makes a nice plot for you. It's going to show us what the relationships look like in the data set. It might take a little while to plot. Probably depends on your computer. Beautiful. Okay. Is it plotting? Okay. So this might be useful in some settings. For example, if you had a population where you knew there were certain relationships. I don't actually know anything about the pedigree in this training population. But if you had a set, for example, a set of full SIB and half SIB relationships in your population, you should see some clusters that look like this. So here the red colors indicate a low relationship, and the yellow colors, the brighter colors, indicate a strong relationship. And this heat map function has a little clustering algorithm that sorts the rows and columns so that close clusters are together. You don't have to worry about that really. But it does have the nice property that you see things like this. So we've got a set of individuals here that are all really closely related to each other. Couldn't possibly tell you why or who they are, but you can see that here. So they should have high values. The diagonal corresponds to inbreeding coefficient. So I can plot that in a second. In fact, so I'm going to make a histogram of the diagonal elements of this matrix so that you can see the values they take. That's a bit lower than I expected. Well, cassava is not supposed to be inbred. All right. And then another thing that you can do is just plot part of the matrix, or not plot, but just look at it so you see what kind of values that you should get.